Hello and welcome to this clip going through our organic chemistry reactions map for the first year of the OCRA syllabus. This can equally be used for the AS specification, but the college that I'm working at we use and just the A-level linear specification. So down the left hand side is a reminder of what particular examples I'll be using when I draw out the mechanisms or the formulae of how to write this out. So what I'll not be doing on this screen is the reagents and conditions, because I'll pull them up on the next screen, as you can see from the bottom of the page. So this page is about drawing out formulae and also making sure that we're using the right mechanism. So if you refer to the key in the bottom left hand corner and just the little phrases on the left of the screen, it'll remind you which particular chemicals I'm using. So I'll start at the top left. So when you draw out the formula for making a polyalkene, or an addition polymer as we call it, you always use square brackets to represent the repeating unit. One repeat unit is 2 carbons, and the trailing bonds should always bisect the square brackets. And finally, don't forget it's an addition reaction, so you get 100% atom economy. Okay, let's move on to alkenes versus alkanes. So the reaction to get from propene to propane, I'm choosing to use propene this time, it's a hydrogenation, so it would use a nickel catalyst at 150 degrees. Again, an addition reaction, and 100% atom economy. So let's now move it to alkanes going to alkenes. So I'll only mention this one briefly because it's not on the OCR new spec, you don't have to go and learn it anymore. So it's catalytic cracking. You might have heard of it at GCSE. So the idea that you break up longer chain hydrocarbons into smaller ones. Perhaps propane isn't the best example to use here. You'd usually get a long chain hydrocarbon, break up into several smaller molecules, one of which will be an alkene, and you may have hydrogen given off, but it's generally when it's removed. In fact, it's more likely to look like the skeletal formula I've now put in the box. So you get a long chain hydrocarbon such as nonane, break up into a small alkene such as propene, and then hexane. But like I said, not on the OCR new spec, so not to worry about this one. So when alkanes react to make haloalkanes, it's through a process called free radical substitution, or just radical substitution. So for example, 1,2-dibromoethane is one possible product. But for every chlorine that comes off, every chlorine that's substituted onto the chain, one hydrogen comes off as HCl. So for that to happen, you have to think quite carefully, in this case, how many chlorines are substituting. There's 2. But you also need to make 2 HCl's. Like so. So you must be careful when balancing your equations. So for each halogen atom X that is substituted, one hydrogen will come off as HX. So remember we said it was a radical substitution mechanism. That has 3 steps. You've got the initiation, which is making radicals by homolytic fission under the influence of UV light. You've then got propagation and termination with their relative descriptions there. So the propagation radical attacks a molecule to make a new radical, and termination is where radicals collide to make a molecule. So provided you have all 3 of those steps in your radical substitution answer, then your mechanism can't go far wrong. So make sure those 3 steps are there, following those descriptions, and you'll be fine. So let's now look at electrophilic addition. If we've got electrophilic addition of a halogen, for example bromine to propene, you get a dihaloalkane. So the bromine adds across the double bond to end up in 2 separate places, one bromine in one place and another bromine in the next carbon along. Now you can also obviously add HBr. So I'm going to look at that one in a second. It's still an electrophilic addition reaction, electrophilic addition mechanism. So if we take our propene and our HBr, what we now do is the mixture of reaction products. So we start with our bromopropane, and we can also make 2 bromopropane. So the first one was 1 bromopropane, the second one was 2 bromopropane. So there's a mixture of reaction products with your hydrogen halide. And Markovnikov's rule will govern which product is more likely. And this in itself is based on carbocation stability in the mechanism, which we'll talk about a little bit later. So looking at the reaction going from haloalkanes to alcohols, this is a nucleophilic substitution mechanism where OH minus hydroxide is a nucleophile. So let's take bromomethane, for example. If we put on our dipoles and put our OH in the vicinity, we can add the lone pairs and put in the curly arrows, not forgetting of course that the species is negatively charged. Now what we can think about is what would take place as a result of this. Now the OH minus goes in behind the carbon of the carbon-bromine bond because the partially negative bromine, repels it. So don't forget your curly arrows, your lone pairs and your dipoles. And finally you can pop in your product, which is methanol, and not forgetting of course the formation of the bromide ion. Now I'll talk about this mechanism in a little bit more detail a bit later on, so I just wanted to do a quick quick show of it now so you can recall the various parts of it that were necessary. Okay, so going the other way, from alcohols back to haloalkanes, it's still a nucleophilic substitution, but the nucleophile this time is a halide ion, for example bromide, which has to be created in situ by this reaction here with solid sodium bromide and fairly strong concentrated sulfuric acid, giving you sodium hydrogen sulfate and HBr in bold there as the source of your Br minus. So to make this reaction work, as in the creation of this HBr, it's carried out under reflux. So moving towards the alcohols again, a bit further down the screen, we're looking this time at oxidizing a primary alcohol to an aldehyde. What's useful to do at this point is to consider the actual change in functional groups. I've put them in bold there, so the OH is the primary alcohol and the CHO is the aldehyde. Now you need to warm this mixture with K2CR2O7. It could be dichromate ions in the form of sodium dichromate, but whatever sort of dichromate you use, you need to distill it because aldehydes have low boiling points and therefore partial oxidation is essential. Now, if a grey box sits in a dotted line, I'm not describing the reaction that line represents. I'm now moving into the area of the screen where there's some dotted lines representing second year reactions. So if you're first year, ignore these. If you're in your second year and doing some general revision, I'll come and talk about these a little bit later. Okay, so the reaction we're going to consider now is the aldehyde going to a carboxylic acid. This is the second half of the oxidation essentially. So we've made the aldehyde by going from a primary alcohol to an aldehyde. Now we're taking the aldehyde and refluxing it a bit further with some more K2CR2O7, again in the presence of H2SO4 as the source of our acid. This would mean the primary alcohol oxidation is now complete. So just to recap, an alcohol going to an aldehyde is partial oxidation, an alcohol going to carboxylic acid is full oxidation. So therefore partial oxidation makes one H2O and uses one oxygen in square brackets. Obviously the oxygen in square brackets is from the K2CR2O7, but full oxidation involves two oxidation steps, so therefore your one H2O is still made, but you use up two oxygens in square brackets to make it balance. So the next one to look at is obviously the ketone. So if you look, you can see there's a black arrow from the secondary alcohol to a ketone. So for this reaction, it's the similar use of an oxidizing agent and H2SO4. So I'll pop the grey box up there for a second. You may think that I've left out the alkenes to alcohol. I'll come back to them in a minute or so. So that's your equation. Again, the secondary alcohol is in the second carbon, uses up one oxygen in square brackets, and produces one water. It produces a ketone, which is CH3COCH3. It's carried out using reflux to try and push it to completion, as always. So the reflux idea is quite important. Looking back to the aldehyde going to carboxylic acid, you can see I've added excess K2Cr2O7 to ensure that the oxidation goes all the way. So if you are hydrating an alkene, you can produce a mixture of alcohols, particularly where the OH is placed. If you have dehydration of an alkene, you get, dehydration of an alcohol, I beg your pardon, you get an alkene and water. And what's important as well is to watch out for mixtures of alkenes in larger alcohols. Let me give an example. So with pentan-2-ol, for example, you could get two possible alkenes, an E and a Z isomer. So in this particular case, you could get three possible alkenes coming off. Okay, so that covers us for all the reactions, I think, on this page. Now we can go on to the next page to have a look at the individual reagents and conditions. So on this page, which you may wish to pause at this point just to maybe take a snap of it or a screenshot or something like that, we have all of the reactions with their appropriate reagents and conditions, plus also the information for the second year reactions that are in pale blue. If you're in your first year, don't worry about these until next year, but they are useful, so if you're in your second year, you may find this useful overall revision. So I'll move on now and have a quick look at the individual mechanisms before wrapping things up. So here we've got the steps for the radical substitution onto alkanes. I'm using chlorine as my example. So the initiation is your creation of radicals by homolytic fission of the Cl bond using UV light. Propagation is your radicals being used up as they attack fresh molecules and then are regenerated. And then in termination, radicals are removed by collision with each other to form fresh molecules. So, like I said, provided every single part of this step is included and you put the right things in, you won't go wrong. So here we're going to look at the three different types or approaches to electrophilic addition. I'm not going to go into the ins and outs of electrophilic addition, but just a general overview. So halogenal alkanes can also be called haloalkanes, and likewise dihalogenal alkanes can also be called dihaloalkanes. So moving a bit further down the page, if we have a look at the asymmetric alkenes, just remembering of course that addition always occurs across the CC double bond. So therefore, if you look at the second one, you get 1,2-dibromoethane, and in the first one you get bromoethane. Bromo doesn't need a number in front of it because there's only one bromine there, so it's only ever going to be on carbon number 1. So, like I said a couple of seconds ago, considering the asymmetric alkenes, what asymmetric actually means is that the carbon-carbon double bond is not centrally located in the carbon chain, so it's towards one end. So you get differing carbocation stability. Primary is carbocations are less stable than secondary carbocations, which are less stable still than tertiary. So tertiary is the most stable, secondary second most, primary least. So the more alkyl groups are attached to the positive carbon atom means greater stability, so that route is more likely to take place. So in the case you've got here, 2 bromopropane is your major product, and 1 bromopropane is going to be the minor product. So what we'll do now is move on to the final mechanism, which is nucleophilic substitution. So here, Nu with the 2 dots next to it represents any species with a lone pair available for a data covalent bond. It doesn't necessarily have to be negatively charged, because obviously water and ammonia are common examples that are neutral. But all 3 of those species have lone pairs, as do halide ions. So they're familiar examples from A-level textbooks. So what's also interesting is to consider the cause of how fast this goes. So the driving factor here is how easily you can break the carbon-bromine bond. So the carbon-halogen bond can be broken, but because this process is endothermic, it's the bond enthalpy that actually dictates this. So the higher the bond enthalpy, the more difficult it is to break that bond, and therefore the slower the reaction will go. So that takes us to the end of this little review of organic synthesis and organic chemical routes. Hopefully it's been useful. I have done a couple of other clips here and there on my channel on some of the individual reactions. If you want to go and have a look at them, you can go onto Jason's Chem Clips. But for now, thanks for listening, and until next time, see you soon.